back to the warm-up. We learned a theorem a couple of days ago, that says when you inscribe a quadrilateral in a circle, we learned something was true about the opposite angles. And we're very careful, it's not the same rule as parallelogram, where opposite angles were congruent. No, we realized the opposite angles together, that angle and that angle, open up to the whole circle. And a whole circle has 360 degrees. And since those are inscribed angles, we divide by 2. So we know that the opposite angles, if you add them together, have to equal 180. 360 divided by 2. So we know that this angle and this angle are supplementary. The biggest mistake you could make is say 2x plus 7y equals 91. So we're going to avoid doing that. Let's make that smaller. We don't need those variables to be that big. Okay, so we're going to start by saying 2x plus 7y plus 91 equals 180. And 7x plus y plus 80 equals 180. So we want to get these into standard form. Okay, Quan, thank you. So that we can solve this system of equations. So we're going to move the 91 over and move the 80 over. So this one becomes 2x plus 7y equals 89. And 7x plus y equals 100. So far all I've done is just moved them over. It's not a bad system, guys. Don't complain. All we've done is move the constant over so that it would be in standard form. Now I notice that none of those are going to cancel. Do you see anything that's going to cancel? Nope. So I recommend we take the second equation and we multiply it by or -7, right? Because we want to be able to add them together. Combination. Add them together and be good to go. So if we multiply this one by -7, then we would get -49x minus 7y equals -700. So that one's gone. And now we can add these together. 2x minus 49x would be -47x. The y's are going to cancel, and that's going to equal -611. At first glance, you're like, oh my gosh, that looks awful. I did something wrong. But no, you take 611 and you divide it by 47, and you're like, phew, oh, it's an integer. Yay. So you divide those, and you get x is lucky number 13. Once you've done that, you've done all the hard work. So then you just take that 13, you can plug it back in right here if you like, wherever you want, but right here would work, wherever you want. And we can get our y. So 7 times 13 is 91. I'm really just plugging in right here. 91 plus y equals 100. And you can do that in your head. 91 plus what equals 100? 9. So x is 13, y is 9. You would write that as an ordered pair. The solution is 13, 9. So technically, Jenny, when you're doing linear combination, technically to solve for it, you're supposed to add them together. But if you want to multiply it by 7 and subtract them, you can do that. But that's not technically how you do linear combination. Does that make sense? You're supposed to add them together. But you know in your head, oh, I could multiply it by 7 and I could subtract them. But that's not combination by technical terms. Checking your homework answers. Angles of a circle, super fun homework. Starting with number 11. AB is tangent to circle O. The measure of AE is, sorry, let's zoom in here. There we go. Arc AE is, oh, not that arc. We want the minor arc, so be careful. We want the minor arc, not the major arc. Arc AE is 160, arc AD is 50, DC is 60, find angle 1 and angle 2. So angle 1, it's all about, hey, where is the vertex? Look at the angle and find out where the vertex is. For angle 1, the vertex is on the circle. So for angle 1, I know out of all my rules, the rule I'm going to use for number 1 is take its arc and divide by 2. Now when I say its arc, I mean the arc, the entire arc that it opens up to. So if you were to follow angle 1 with your hands, if you were to follow it, you notice that it is opening up to an arc of 110 degrees, 60 plus 50. So if its arc is 110 degrees, then the angle is 55 degrees. All right, angle 2. Where is the vertex of angle 2? The vertex is not on the center, it's not on the circle, it's somewhere in the interior of the circle. So we're going to use our new rules. We're going to add the arcs and divide by 2. When I say add the arcs, I mean the arcs that it opens up to. You follow it with your fingers. So that angle 2 is opening up to that purple arc and that purple arc. So I know one of the arcs is 60. I don't know the other arc yet, so I'm going to do 360 minus, do you see that teal one? 160. If I do 360 minus 160, I'll have that major arc that I can't name because they didn't give me another letter. So this arc that I just found is 200. Add your arcs and divide by 2. So 60 plus 200 divided by 2. And that's where you get that angle 2 is 130. Okay? Next one, number 19. All right, we had some good problems in this section. I hope you tried these. Tell me you tried these. Number 19 was one of the theorems we learned. You don't have to use the theorem, but it's really handy. The theorem said if an angle is inscribed in a semicircle, it's a right angle. Where that theorem came from was that if this angle is opening up to the diameter, then the arc that it's intercepting is 180. And every time you take a semicircle, you take 180 and you divide by 2, you're going to get 90 every time. So what this is saying is that angle Y, angle X, and angle Z are all 90 degrees because all three of those angles are inscribed in a semicircle. All three of those angles are opening up to the diameter. Every time you divide 180 by 2, you're going to get 90 each and every time. So all three of those angles are 90-degree angles. Follow it with your finger. Oh, if I follow this one, I'm opening up to the diameter. If I follow this one, I'm opening up to the diameter. So that was a good question, number 19. They're all good questions. 22, and then 26. 22. Lots of stuff going on, but it's not going to be too bad. Let's find what we want to find first. Ooh, we've got some parallel lines. That's what those arrows mean. So we're probably going to use that. If we use parallel lines, we know that we can use alternate interior angles. This angle and this angle are alternate interior angles. So that means that they are congruent. So I wrote an X in that other angle because it's congruent to the angle X. Now I can find angle X. I know that an inscribed angle, because its vertex is on the circle, An inscribed angle is half the arc. So I take 100, I divide it by 2. So x is 50. This angle is 50, which makes this angle 50. 50, 50. Alternate interior angles. Oh, now I know a arc y. Now I know arc y. Arc y is also 100 because I take the inscribed angle and I double it to get the arc. So arc y is now 100. Now I can find the last arc of the circle that we weren't sure about. Now I can find that purple arc by adding up the arcs and subtracting from 360. So that would be 290. 360 minus 290 gives us a 70-degree angle. For angle Z, find out where the vertex is. The vertex is on the circle. So we treat it just like an inscribed angle. We take Z's arc and we divide it by 2. We take 70 and we divide it by 2. All right. Did I clear that one up? Hope that one makes sense. You had to use those parallel lines to help you out. Alrighty, next one. 26. Oh, you threw one at me in this big circle. Okay. Okay. No, it's not difficult. It's actually really fun. I don't know if you tried this at home, but these circles are really fun because one thing and you find the other. It's like a puzzle and you're solving it, and I love these things. I could do these all day. All right, the measure of arc AB is 80. The measure of arc BC is 20. The measure of arc DE is 50. And you're wanting me to find angle 3. All right, that's not bad at all. Every time you ask yourself, hey, where is the vertex of the angle that I'm looking for? Where is it? Is it inside, outside, on, or center? Inside, outside, on, or center? The vertex of angle 3 is in the interior of the circle. So I use the rule that says, add my arcs and divide by 2. What arcs is angle 3 opening up to? Follow the rays. Follow the rays. So it's opening up to 80, and it's opening up to 50. So you just add them up and divide by 2. Do you want me to find any other one of those angles? I can keep working more of it, but I don't want to if we all know how to do it. Speak now or forever hold your peace. So it was kind of confusing how this was marked. They wanted this one to be angle 9, and they wanted this one to be angle 6. That's why they put that arc there. They wanted that to catch the whole angle. Sorry, I'm going out of focus. So angle 6 is super easy. It is what it looks like. Doesn't that look like a right angle? Well, it is a right angle because that is an angle inscribed in a semicircle. Look. That's the diameter. Anytime you've got a triangle that's inscribed in a semicircle that opens up to a diameter, it's a 90-degree angle. So that one is exactly as it looks. But you might have been confused because it was marked kind of weird. What other angles do you want me to do? Okay, so now if we're looking at angle 10, I know the way that I'm going to get it. I know that I'm going to find this arc, and I'm going to divide that arc by 2. But I don't know that arc yet. So I'm looking around to see what I can do. One thing, this might not be the only way to get it, but one thing that I can do is I see a semicircle. Do you see that semicircle? EDB. I'm trying to pick a color I haven't used. EDB is a semicircle. And so now I can find that purple angle because I can do 180 plus 80 and subtract it from 360. Okay, so you get 100. Okay? So now I know that that arc is 100, and so angle 10 must be 100 divided by 2. Is that okay? You always are looking for, if I want an angle, I better find the arc that it's opening up to, because that's going to be your key. Is DA a chord? Sure. Go ahead and title your notes, Segments of Circles. Now, it's really misleading because we are not studying these, because I told you this was a segment of a circle. We're actually not talking about that. We're talking about the different segments that you can draw in a circle. Okay, so title's kind of misleading. But anyways, take it for what it is. That's what we chose to call it. So, I'm just going to dive right into the theorems. We're not going to derive them. Please don't write all these words. I would draw the picture and I would write the formula. That's what I recommend. If you want to watch it later and write all the words, you can watch it later. All right, so what do we have here? We are away from angles. Put angles out of your brain. We are back to how long is the segment. We're back to lengths, okay? So what this theorem is saying is if I draw two chords in a circle, any two chords anywhere you want in the circle, something cool happens. So what happens is that, let me call this X, let me call this Y, let me call this W, let me call it Z. So what happens is that they don't really bisect each other. There's no rules because you can put them anywhere you want in the circle. So the cool thing that happens is the product of the different segments you get, X times Y, equals the product of the segments you get from the other line. So part times part equals part times part. So that's what our first theorem says. Remember, we're learning about 3 theorems a day. I call it our 3-theorem diet. So we're going to learn 3 theorems today, believe it or not. Okay? So part times part equals part times part when the chords are in a circle. X times Y equals W times Z. AE times EC equals DE times EB. Did I say that in enough ways? Okay. Let's start off and try a super easy one. Alright, so what we learned was the part times the part of one of the chords equals the part times the part of the other chord. This is almost kind of like proportions. You're almost cross-multiplying. But just divide by 6. Final answer, X equals 10. So that's just a really basic application of how this works. So it's kind of like you're saying 12 is to 6 as X is to 5. All right, let's try another one. AE is 8, CA is 12, BE is 5, find BD. All right, so let's go over it. So we know the theorem says the part times the part equals the part times the part. So what we're going to need to do is come up with some parts. So the first thing that I would do is take 12 and subtract 8 to get us 4. Not drawn to scale, right? Not drawn to scale. All right, and then when we do our formula, we're going to be finding ED. We're not going to be finding BD, but that's okay because we can just add 5 to it. So the part times the part equals the part times the part. So you do 8 times 4 divided by 5. And you get an answer, but be careful, that answer is X. And if we want BD, then we need to add 5 to it, segment addition. So when you take that answer and you add 5 to it, you get 11.4. Or if you would like fractions, 57 fifths. Yeah, a lot of you just put what you got for X and you didn't add it back together to get BD. Oh, that's okay, Jenny. We're looking to see what we see here. And we're talking about segments. We're talking about segments, not angles. So we already did angles yesterday. So what is AB? What is it? It's a chord. Very good. AB is a chord. What is AC? Kind of a secant, except it's not really a line because it doesn't go on forever. What would you say is the external part of AC? Name it. Name it with letters. A really long chord. No, a chord has to have endpoints on the circle, so it's not a really long chord. Good job, Tahani. Okay, tell me what proportion you used. So what's the external part of AC? Because we need this word for the theorem we're about to use. What would we call the external part of AC? Yeji, try scrolling down. No, we're not finding any arcs, Taha. Right now we're just talking about how to name these segments. So what I'm saying is that I would name this one, in the theorem we're about to learn, we're going to call this the whole segment. And I'm asking which part would be the external segment. AB is the internal. So very good, Jenny. BC would be the external. So we need to know what I'm saying when I say external. We're going to need to know what I'm saying for this next theorem. So here's theorem number 2. Theorem number 2 out of 3 for the day. Oh gosh, we're almost out of time. If 2 secants are drawn, then the product of the length of one secant segment and an external part equals the product of the other secant segment and its external part. So really what I'm saying, and what you should probably memorize, whole times external equals whole times external. Whole times external equals whole times external. So AC times BC equals EC times DC. EC DC. Doesn't that mean they're congruent? What's there? Nope. Their product is equal, but not the segments. Okay. We're going to have to get going because I didn't realize where we were on time. So let's just get started. Whole times external equals whole times external. So you need to find the whole, 12. Whole times external equals whole, oops, I meant to put plus, times external. Whole times external equals whole times external. So 36 equals 16 plus 4x. 36 minus 16 divided by 4, and so we solve for x and we get 5. And you can always plug it back in to make sure it works. Whole times external equals whole times external. Alrighty, AB is 2, BC is 6, EC is 15, and DC is x. So this one is almost easier than the one we just did. Ready? Whole times external equals whole times external. Whole times external equals whole times external. How many times can I say that in a row, right? So 8 times 6 divided by 15. What do we get? Y'all getting 3.2? Good. Okay, last theorem. We just had to make it to this theorem. Okay, so here's the other situation we could have. We could have a secant and a tangent. What do we do to find that segment? Okay? I want you to think of this as the same as the theorem we just learned, except in this theorem, the whole is the external. The whole is the external. So when you do whole times external, you're really just doing external squared because they are one in the same. So this is really the same theorem as the last theorem. We kind of call it like a corollary, but the whole is the external for that tangent segment. So I'm writing tangent squared equals whole times external, but it's still the same formula, whole times external equals whole times external. Give you a second to write that down. Okay, so now we need to give this theorem a test run. So the theorem says the tangent squared equals the whole times the external. The tangent squared equals the whole times the external. So we've got 36 equals 5x plus x squared. Uh-oh, that's a quadratic. 0 equals x squared plus 5x minus 36. Things that multiply to get 36. 6 and 6, that's not going to help us. 9 and 4 will help us. We want the 5 to be positive, so we're going to want the larger one to be positive. And then when we solve for x, we get x is 4 and negative 9. In geometry, do we have negative segments? Can a segment have a negative length? No, sirree. So we throw out the 9. I'm sorry, I'm answering my own question. And x is 4. Next one. Whole times external equals tangent squared. Tangent squared equals whole times external. This one we're not going to have to factor because we don't have an x value, so we are pleased with that. X squared equals 44. X equals the square root of 44, which is 2 root 11. Doing okay? Sorry, I'm going fast. Oh, we made it to the end. Look at that.